Hi guys. So week 3 of school closure, and this is lesson 1. So hopefully there isn't a week 4, that we're all back next Monday in school. But either way, our second lesson of the week will be a live one. So what we'll do is we'll have a look at the work that I gave you last week. And then we're going into a bit of chemistry, and there's quite a bit in this. And to be honest with you, it's quite a practical part. Now, obviously, we can't do the practical bit at the moment, but we'll do our very best with the theory. So at least that's done and dusted before we go back to school. Okay, so we'll go back and look at the OneNote, which you have access to yourselves. And we're moving on to January 25th. So we're moving on to the third week. And if we go and have a look first off over here, this is just some examples I've taken of the work that I snapped out of people's homework folder. Just the kind of thing that I was looking for when I asked you to look at preserving the different food types and the history of preserving food and so on. So I've taken these off a few different people's work from their homework folder. So why you use preservatives, what the harm of preservatives could be. So that's in your OneNote to have a look, just in case you haven't uploaded yours yet. You can take ideas from other people's. So there's some of the history of preservation. Things like pickling's a great one. I think there was salting mixed as well, mixing with Princeton honey. There's lots of them there. Heating, fruit and sugar. Loads of salt, great ways of preserving. Here's an example of someone who looked into tuna. So it's heated in the planter factory, and then they're pressurized, which stops air from entering. Air is what causes bacteria and fungus to be allowed to grow. So, as we said, 3 to 5 years once it's preserved properly. Here's one of the last slides. Is it bad for us or good for us? So some better than others. Freezing obviously is not. Most of you have a freezer in your house, but chemical preservatives can be worse. Example of the milk one. So pasteurization. So you heat the milk to 72 degrees and hold it at 72, 15 seconds and then cool it. This makes it almost sterile. So you're killing all the baddies in the milk, and then you can keep it in the fridge for a few days. So that's there for you to take a look at. And here's a slide about what happened before preservatives. So think about hanging meat and how you kill the viruses and bacteria. So there's lots of different examples of people's work there. This is an interesting one I just took off someone's work. Preservation of crisps. So they're infused with nitrogen, and nitrogen stops bacteria, fungus and viruses from growing in, and it also stops the crisps from going soggy. So some great examples there of work, and if you haven't uploaded yours, make sure you do so as soon as you can. Okay, so that's last week's work. Okay, going back to this week, and to start off, what I want you to do for the first couple of minutes, and you're going to have to pause the video in a second to do these two links here. So there's link 1 and link 2. These bring you into simulations. So simulations you can mess around with. They come from a place called FET, so the University of Colorado. And I've actually opened one of them, so I'm just going to show you one for a second. And this is the one on solids, liquids, and gases. So basically, if I go over here to the right and I hit water, so there's oxygen, there's water, and I say, right, if I put my cursor, raise the temperature, look what happens to the particles. And you see what happens to the particles. They all start to get energy and move around. And if I cool them down, they stop moving, they come together, and it's all they can do is vibrate. So this is looking at how particles we can't see, really, 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 really tiny, how they act under different temperatures, and why ice is different to water, is different to steam. So there's ice, there's water, and finally it starts to become steam when they're no longer together and they can float off into the air. So there's a simulation I want you to mess around with. And you have loads of different things over here on the right, liquids and gases. It'll change them for you. And there's argon and oxygen and so on. And just to kind of get an idea of what we're going to, down the bottom here, in the bottom part, you can see the phase changes. So you can add pressure to it, or add water to it, even not pressure. As you add more particles, the pressure should go up. We could add more heat. How does that affect the pressure? And we can change them all around. So there's something for you to have a play around with. See, can you make sense of what we're looking to show? The other one I'll leave you to have a go is the behaviour of how gases behave. So there's two simulations there I want you to have a mess. So if you pause the video now and give it 5 or 6 minutes to have a go of both of those simulations and see can you make head or tail of what they're trying to teach you. Okay, right, so let's go into some of the theory behind this. The first off, this word, you'll come across it all the time, matter. So matter is anything that takes up space and has a mass. Remember, mass is the same as weight, except it is not dependent on gravity. So matter, the definition is anything that occupies space and has a mass. So if we go down here and we have a look at this gas jar here, so see this here, this is basically an upturned glass, and all in here is full up to the top with water. And this guy here blows air from his lungs through a straw, and it bubbles up through. And now up in here, you don't have water anymore. You have the air that came from his lungs. And what you're looking to show is that this is occupied space. So sometimes if I asked you what's in that spot there, you'd probably say nothing. But there is something. It's just not water anymore. It's a gas instead. And it's the same over here. If you weigh a balloon with no air in it, it's 1.63 grams. If you put air into it and weigh it again, the weight will go up because air is matter as well. So it has a mass. So what they're saying is that gas has a mass. So the gas weighs something. Right, now, going on to this, the 3 states of matter. So the 3 ways that matter can exist are solids, liquids, and gases. So you can have things that are solid, you can have things that are liquids, and you can have things that are gases. And most of them can be all 3. If we take the example of water, water can be a liquid that you drink, it can be a gas, it can be a solid. We'll go through those in a few minutes, but that's probably the one you know. Solids, if we're to put this into notes, solids have a shape. So if I was to say, is your desk a solid, liquid, or a gas? You'd say it's a solid, sir, and I'd say it is. And why would you say, well, why is it, how would you classify it as a solid, or why is it solid? Well, it has a definite shape. If your desk was made of liquid, it probably wouldn't have a definite shape. It would have definite volume, so it's very hard to compress a solid. It usually means that you can't squeeze it into a smaller size, and they don't flow. Solids don't flow. I'm not going to be able to pour a desk into into another room. I have to actually pick it up and move it. So they don't spread over a surface. They just stay in the one spot. Liquids then, if we compare these, liquids have no shape. Liquids have no shape at all. They take the shape of whatever they're put into. If I put a water into a conical flask, it will go in a triangular shape. If I put it into a beaker, it would be like a cube or a cuboid. They do have a definite volume, same as solids. Very difficult to compress them, very difficult to push them into a smaller spot. And they do flow. So a couple of properties of solids and liquids. Gases, however, have no shape. Obviously, they're gases. They have no volume, so you can compress them. See, so you can compress them. And they do flow as well, same as liquids. So they're just the difference of solids, liquids, and gases, the properties. Okay, and here's what they look like on a small scale. So if you have a look at a solid, all this is in a nice fixed shape. See that nice shape of the solid? So it's in a nice fixed shape. All the particles are in a fixed position. In a liquid though, see, they're all over the place. So they're kind of quite similar, to the solid, but what the particles can slide over one another. That's how it enables them to flow. This one can't flow because they're all stuck in a fixed pattern. Gases down here, the particles are far apart. So they're all moving around into whatever space that's available. Okay, so the particles moving around. So here's your solid, here's your liquid, and here's your gas. That's what the particles look like. In here is all you're getting in a solid is that you're getting a bit of vibration. That's all. So these particles here are kind of vibrating to and from in the solid. Okay. This word here, diffusion, another definition, is the spreading out of material due to the movement of their particles. Works with liquids and works with gases. If you have a look at this teacher here is spraying a can of Lynx up at the top corner of the board. It could be a kind of fly spray or something. And someone down the back, after a minute or two, will say, I can smell that. Even though it was sprayed up in the corner, I can smell that. I can smell that Lynx or Sure Some Zebra or Sensitive, whatever you're using. And because of that, the reason you're smelling that is because liquids and gases have the ability to flow. Okay, so they can flow, they spread out in the air from an area to another area. So if you're to get a stink bomb or something and you're to throw it in the bathrooms, after a while, that the gas particles are going to spread out and they're going to move, and that is diffusion. Chinese takeaways use this to great effect. They will have a fan in their kitchen that vents the smell of that lovely curry chip smell out into the car park. So you're walking by and you get, and the gases have diffused out into the car park and you get that lovely smell and it makes you want curry chips. So that's diffusion. So you can have a good example of the curry chips. You can have an example of the Lynx or fly spray. That is the gas particles moving around. Okay, don't worry about this for a moment. Now, so if we stick with solids, liquids, and gases, so we stick with those three things, right? So there are three. There's number one, there's number two, and there's number three. And we will say, how do we get from solid to liquid, liquid to gas, and gas to solid to liquid, liquid to gas, and backwards? So if we say that we have a solid over here, a solid here, a liquid here, and a gas here. So there's the three. I know it's a solid and so on. Don't worry about that. But if we have a solid, a liquid, or a gas, how do we get from a solid to a liquid? What do we have to do? If we stick with a water example, how do I get from solid water, what's the fancy name for solid water again? Ice, to a liquid? There's your answer there at the top. They've put it in, but we'll write it in the... You melt it. How would I get from a liquid to a gas? What would I have to do to get from a glass of water to water and gases from water vapor? It's two words. One is the word in science we generally use boiling. In geography, you might have heard of the word evaporation. Evaporation to a gas. What about the other way? The other way might be slightly more tricky. What if I want to go from a liquid back to a solid? I would have to, how would I make ice? How would I go from a glass of water and turn it into ice? I'd stick it in my freezer, wouldn't I? And I would have freezing. But the one that they always ask, because people can never think of it, how do I go from a gas back to a liquid? So I'm thinking, I'm in the car, I'm going to school, cold morning, and the windows start to fog up. Why are the windows fogging up in the car? And so it's something to do with breathing. So you're breathing out nice warm air, nice warm gas, and it's turning into a liquid, and it's sticking to the windows and blocking the window. Whenever it's driving the car, then has to put on the hot air to clear the windows again. What's that? What do they say it is? It's called condensation or condensing. And that's how you go from a gas back to a liquid. And I think I put these down for you. A couple of words to add on. The melting point is the temperature at which a solid changes to a liquid. So you can look this up. If we're to take the example of ice, what's the melting point of ice in degrees Celsius? The other one, what's the boiling point? So melting point, what's the boiling point of water? In degrees Celsius. They're your two most important numbers. One is what temperature does ice melt to become water, and what temperature does water boil to become water vapor. This last one, a small number of solids change directly from a solid to a gas when heated. I love this experiment. It's a real science week one that we will do next year when all these restrictions and all are gone. Sublimation. A great example of sublimation, I bet you've all heard it before, is dry ice. Dry ice doesn't go to a liquid at all. It goes straight from a solid to a gas. And that's what sublimation means. So it skips the whole liquid thing. It turns from a solid into a gas straight away. Okay, and a small bit of geography. So a really small bit of geography, and one that will come up in the geography course as well, is just this definition of evaporation. Changes from a liquid to a gas at the surface of the liquid. So this is how water doesn't have to get to 100 degrees all over in order to evaporate, because we know the surface outside is at 100 degrees, yet the rain seems to dry up. So evaporation is when it just changes to a gas at the very surface. Okay, boiling is the same. Boiling is the same idea. So I asked you for the boiling point of water, but the definition is the boiling point is the temperature at which a liquid changes to a gas throughout the liquid. So you can see these two definitions. Boiling has to change throughout the liquid, whereas evaporation is only at the surface of the liquid. And all these kind of experiments are ones that we're going to be doing when we finally get ourselves back into the lab. This is what we would usually do, would be melting and boiling and evaporating and condensing and all this kind of stuff, which we're kind of prevented from doing at the moment. Okay, and this we already spoke about. Condensation is the changing of a gas to a liquid. So condensation is the changing of a gas to a liquid. But what I've put down here is the whole lot for you. So all this here is a long version of what this is trying to tell you in this. And this is the most important. I'm going to put NB beside it. NB, very important. And this is how you change between a solid, a liquid, and a gas, which we explained earlier on. So here's your ice to your water to your gas. Remember, the key words are going to be melting, boiling, condensing, and freezing. And this is what it would look like in real world. This is the important part of what's happening at a particle level. So remember, these are this is your solid, your liquid, and your gas. In here, the particles are just vibrating, but they're fixed. In liquid, they're sliding over each other. And in gas, they're just moving, flying around the place in all random directions at high speed. That's your solids, your liquids, and your gases. Okay, I know that was kind of quick. You might have to, as well as looking at those two simulations, you might have to go through that yourself nice and slowly and maybe summarize it for your notes in your notes copy. And what I want you to do is I want you to try these couple of questions. There's only a few. There's about 10 minutes work in it. So I want these uploaded to your homework section of your OneNote before our second class of the week, which will be a live lesson. So I'll make that really, really bright in your OneNote so you can see it. And we will correct those at the start of the next lesson and move on. But if in the meantime, if any questions at all about solids, liquids and gases, and diffusion and melting points and boiling points and the properties of solids, liquids and gases, just send me an email or give me a shout. Or if you can't do any of these questions, stick it in a comment on Schoology or email me directly, but I don't think you'll have too much problem. Thanks. Have a great week, everyone. Talk to you.